This is part 3 of lecture 2.4, More Examples of Proofs. In this video, we will give additional examples of proofs of results on divisibility of integers. Assume throughout that all variables are integers. Consider the claim, if P is prime and P divides AB, then P divides either A or B. This is a conditional sentence with antecedent P is prime and P divides AB, and consequent P divides either A or B. We will give a direct proof of this statement. Assume that P is prime and P divides AB. Since the consequent is a disjunction, we will include in the hypothesis the negation of one of the statements in the consequent. In our case, we assume that P does not divide A. We need to show that P divides AB, that is, B is the product of P and some integer k. To show this, we will give a specific number k, verify that k is an integer, and show that B is equal to P times k. We will use the following results. If P is prime, then the GCD of P and A is P if P divides A, and the GCD of P and A is 1 if P does not divide A. The proof of this result is left as an exercise. The smallest positive linear combination of A and B is the GCD of A and B. This was proved in example 7 in part 2 of lecture 2.4. If C divides both A and B, then C divides A plus B. This was proved in example 1 in part 1 of lecture 2.4. And finally, if C divides either A or B, then C divides A times B. This was proved in example 2 in part 1 of lecture 2.4. We now give the complete proof. Assume that P is prime, P divides AB, and P does not divide A. By exercise 10, the GCD of A and P is 1. By example 7, the GCD of A and P is a linear combination of A and P. Putting these together, we get that 1 is equal to AX plus PY for some integers x and y. Since B is equal to 1 times B, we can write B as AX plus PY times B, which is equal to AB times X plus P times YB. Since P divides AB, it follows from example 2 that P divides AB times X. Since YB is an integer, it follows that P divides P times YB. Hence, P divides both terms in the sum. So by example 1, P divides AB times X plus P times YB. Therefore, P divides B, which completes the proof. Consider the claim if Q has the property that for any A and B, the number Q divides either A or B whenever Q divides AB, then Q is prime. Here, Q is assumed to be greater than 1. This is a conditional sentence with antecedent. For any A and B, the number Q divides either A or B whenever Q divides AB, and consequent, Q is prime. For a direct proof of this statement, we begin by assuming that Q is greater than 1, and that for any integers A and B, if Q divides AB, then Q divides either A or B. We need to show that Q is prime, or equivalently, for any positive divisor D of Q, either D is equal to 1 or D is equal to Q. To show this, let D be an arbitrary integer and assume that D is positive, D divides Q, and that D is not equal to 1. we will show that D is equal to Q. We will use the following results, whose proofs are left as an exercise. If A and B are positive integers and A divides B, then A is less than or equal to B. If A and B are positive integers such that A divides B and B divides A, then A is equal to B. We now give the details of the proof. Assume that Q is greater than 1 and that for any integers A and B, if Q divides AB, then Q divides either A or B. Let D be an arbitrary integer. Assume that D is positive, D divides Q, and D is not equal to 1. We are to show that D equals Q. First, note that Q equals Q times 1, so Q divides itself. Since D divides Q, the quotient Q over D is an integer. Since Q is the product of D and the integer Q over D, and Q divides itself, it follows that Q divides the product D times Q over D. Hence, by the hypothesis, Q divides either D or Q over D. Observe that the disjunction either Q divides D or Q divides Q over D is equivalent to the conditional sentence, if Q does not divide Q over D, then Q divides D. So, to prove that Q divides D, we will show that Q does not divide Q over D. We will do this using proof by contradiction. Suppose that Q divides Q over D. By the above, Q over D is a positive integer. So by exercise 2, Q is less than or equal to Q over D. Multiplying both sides of the inequality by D over Q and simplifying, we obtain the condition D is less than or equal to Q over Q, which is equal to 1. Since D is a positive integer, this means that D equals 1. So both D is not equal to 1 and D equals 1 hold. Contradiction. Therefore, D does not divide Q over D, and it follows that Q divides D. This, together with the hypothesis, shows that both conditions, Q divides D and D divides Q, hold. Since both D and Q are positive integers, it follows from exercise 3 that D is equal to Q. This proves that Q is prime. Consider the claim the square root of 2 is irrational. This is equivalent to the statement the square root of 2 is not equal to the quotient of two integers, which is the negation of the statement for some integers p and q, the square root of 2 is equal to p over q. The proof that we will show is attributed to Euclid and is a proof by contradiction. It begins by assuming that the square root of 2 is rational. A contradiction is deduced, which then implies that the square root of 2 must be irrational. Here are the details. Assume that the square root of 2 is rational. Then, by the definition of a rational number, the square root of 2 is equal to the quotient p over d of some over q of some integers p and q. Note that either p over q is in lowest terms, meaning the GCD of p and q is 1, or it is not. If it is not in lowest terms, meaning the GCD of p and q is greater than 1, we can cancel the GCD of p and q in the numerator and denominator to reduce the fraction to lowest terms. Thus, if the square root of 2 is a fraction, then the square root of 2 can always be written as a fraction in lowest terms. Hence, we can assume without loss of generality that P over Q is already a fraction in lowest terms. That is, the GCD of P and Q is 1. Squaring both sides of the equation, the square root of 2 equals P over Q, yields the equation 2 equals P squared over Q squared. So P squared equals 2 times Q squared, which means that P squared is even. We will show that P is even using proof by contradiction. Suppose that P is odd. Then P can be written as 2k plus 1 for some integer k, and P squared is equal to 2k plus 1 squared, which is equal to 4k squared plus 4k plus 1, which is equal to 2 times 2k squared plus 2k plus 1. Since the sum and product of integers is an integer, 2k squared plus 2k is an integer. Thus, P squared is odd. But by the above, P squared is even, so P squared is both even and odd. Contradiction. Hence, P must be even. Continuing, we can then write P as 2 times m for some integer m, and thus Q squared, which is equal to P squared over 2, is equal to the square of 2m divided by 2, which is equal to 4m squared over 2, which is equal to 2m squared. So Q squared is also even. By an argument similar to the one above for P, Q is also even. Note that we will not repeat the details of the argument here, because we will use exactly the same statements, except with P replaced by Q. This shows that both P and Q are even. That is, both P and Q are divisible by 2. So 2 is a common divisor of P and Q, which implies that the greatest common divisor of P and Q is at least 2. Hence, the GCD of P and Q is not equal to 1. But we assumed that P over Q is in lowest terms. Thus, we have that the GCD of P and Q is both equal to 1 and not equal to 1, a contradiction. Therefore, the square root of 2 is irrational. You have come to the end of Part 3 of Lecture 2.4. Before you proceed to Part 4, you are strongly encouraged to do the exercises given at the end of these slides. Thank you for your attention.